Hello and welcome to this lecture. We are going to study very quickly about trigonometric identities and importantly about an idea called roots of unity. Now trigonometric identities are very standard, you would have learnt it from school. I just want to quickly show you that and how it comes from the complex exponential. And importantly, we will move to this roots of unity. This roots of unity is something you are learning very early on in this program, but then later on when you study Fourier transforms, discrete Fourier transforms and all of that, the roots of unity will come back very strongly. So at that time you can try and remember this. I'll introduce you to these ideas very briefly in this short lecture. Okay, let's get started. So these are some of the really famous, very basic identities, and I just want to show you how easy it is to derive these things once you know the complex exponential. So you know e power I into a plus b is e power I a into e power I b, and that's all you need to know. Now e power I theta is cos theta plus I sin theta. You use that here. Now you have a natural product here. You can multiply these two. You see you get cos A cos B, and then cos A I into cos A sin B. You get that here. And then I into sin A cos B, which you get here, and then I squared into sin A sin B. Now I squared will become -1, so you just get a minus here. So you see naturally you get a real part, imaginary part, and you can match up the real part and imaginary part. There is equality between these two, and so that implies cos A plus B is cos A plus B is cos A cos B plus minus sin A sin B, and sin A plus B is sin A cos B plus cos A sin B. So very standard inequalities, equalities and identities that you have in trigonometry. Okay, so you can also do other things like cos 2 theta sin 2 theta. These are formulae that you learn very quickly, and then that's just e power I into 2 theta is e power I theta squared cos theta plus I sin theta squared. I'm not going to go into detail here. You can just square this term by term and you will get the real part will become cos square theta minus sin square theta. The imaginary part will be 2 sin theta cos theta. It's quite straightforward. You can even do sin 3 theta cos 3 theta. There are various ways to do it. I'm just showing you the complex exponential way. You just write this whole cubed and then you identify the real part and imaginary part. You get these identities. So in short, you can do all bunch of trigonometric identities. There are many more like this involving sine and cos. So you can find all of them by connecting to the complex exponential. Okay, so the other sort of important thing about sine and cos is what happens when you add pi by 2 and pi to the arguments. So here is a very interesting and simple relationship. Cos pi by 2 minus theta. So you have an angle theta. You are measuring cos theta, and then you can also measure pi by 2 minus theta, right? So what would be cos pi by 2 minus theta? It turns out it's the same as sin theta. So sin pi by 2 minus theta is the same as cos theta. So sine and cos are very intimately connected and simple, very closely related functions. They're not very different functions actually, right? So I'll show you a picture later on, but you can see how cos pi by 2 minus theta becomes sin theta, and sin pi by 2 minus theta becomes cos theta. And the proof is also very easy. There's a mistake here. This should be e power I into pi by 2 minus theta. So maybe I should just correct that. Okay, so the proof for these identities is quite simple. E power I into pi by 2 minus theta is all you have to look at, and then you use the multiplicative property here. You see that's e power I pi by 2 times e power minus I theta. And what's e power I pi by 2? E power I pi by 2, it's just I, right? So it's just I. So I into cos theta minus I sin theta, right? This is e power minus theta. So e power minus I theta. So that is e cos theta minus I sin theta. And then you multiply by I, you get I cos theta minus I squared sin theta. So now minus I squared is plus 1, so you get sin theta. So it's very easy to prove these things. And there's a variety of things you can prove around pi by 2 and pi. So this is what happens, for instance, if you do I pi by 2 plus theta. So very similar proof will show you cos pi by 2 plus theta is minus sin theta, and sin pi by 2 plus theta is cos theta. So another way to visualize all these things, you can visualize on the unit circle. So you have an angle theta, you add a 90 degree to it, the cos actually now becomes the sine of the original angle, and the sine actually becomes the cos of the original angle, and there is a sign change, and you can prove these even geometrically looking at the unit circle and the angles. Okay. So something also happens if you do pi. Now e power I into pi minus theta, if you do that, and you can use e power I pi is -1, and you will get this kind of relationship. So you see cos pi minus theta is minus cos theta. So when you do pi, the function itself does not change. Cos doesn't become sine, sine doesn't become cos. It retains itself, but then the sine alone respects the sign of cos in that particular quadrant. So cos pi minus theta minus cos theta, and sin pi minus theta sin theta. Likewise, you can also do cos pi plus theta as minus cos theta, sin pi plus theta as minus sin theta. Okay, so these are all pi by 2 relationships. So all this should convince you that sine and cos are really translates of each other. You can move sine around, and then when you shift it left side or right side, you're going to get cos again, and that's our very close relationship to cos or minus cos or something like that. Okay, so this you can actually show like I've shown here. So for instance, in this picture, I'm sort of visually showing that sine and cos are related to each other, right. So in this picture, I have shown cos, right. This is cos theta. You can see it's 1 at 0 and 0 at pi by 2, 0 at minus pi by 2, minus 1 at pi and minus 1 minus pi. So you see this is cos theta. Now if I start moving the cos theta to the right, okay. So I'm shifting cos theta to the right. I'm slowly shifting. You see it just keeps moving away, but you see that wavy nature is sort of the same. And let's just go up to pi by 2, right. So initially we were here, right, we were on top, and I'm going to move slowly by pi by 2. Pi by 2 means this curve will come close to 0, right. So you notice here now this red is exactly sin theta, okay. So I started with the cos and I kept shifting right by pi by 2 and I got sin. Okay, this is the same as what we saw before, cos theta minus pi by 2, cos pi by theta minus pi by 2 is going to become sin theta. Okay, so that this is the logic for that, and you can see visually that this is true, right. So this is gone to sin. So this is up to pi by 2. Now if I shift up to pi, if I do cos pi, you will see that you will get minus cos. Okay, so now I have shifted cos all the way up to pi, right. So this point has come from minus pi by 2 to pi by 2. So I have shifted by pi, and now I get minus cos. So you see how the blue and the red are minus of each other, right. So you multiply blue by minus 1, you get red. Okay, so this is at pi, and then you can keep going. If you keep going, if you go to 3 pi by 2 or minus pi by 2, you will see you get minus sign. Okay, notice this is minus pi by 2. I've shifted right by 3 pi by 2, which is the same as shifting left by pi by 2. So you can visualize, I'll show you the other way around also, what happens when you shift left. So this I've shifted right by 3 pi by 2, and I end up getting minus sign. Okay, and then I can shift further right, and from 3 pi by 2, if I go to 2 pi, there's no surprise, at 2 pi I will get cos again, because cos theta plus 2 pi at 2 pi is periodic, right. So it goes up to cos pi again. I'll show you the other way around. So you see the left shift by the other way around is also the same. So I shift to the left by pi by 2, I get minus sign, right. So I get minus sign here, and then I shift by pi, I get minus cos. Okay, minus pi is the same as plus pi. So whether you shift right or left, you get the same minus cos here. And then you do pi by 2, which is the same as minus 3 pi by 2, you get sine. Okay, you get sine here, and then finally if you go all the way to 2 pi, you're going to get back to cos. Okay, so you can play this if you like, and then watch this to set it in your mind so that it moves on from here to there and then back. Okay, so I hope this is clear to you. So that's how this works. So basically sine and cos are translated versions of each other. So in some sense there is there's no real reason to define both of them, but then both of them are sort of complementary to each other. So one defines the other and all that. So it's very, very good to have both of them studied. Okay. Okay, so let's move on. Okay, so that's about trigonometric identities. So just a quick recap to show you what you should already know from school. Okay, now we move on to this roots of unity. This is an important idea. It's good to set it in your mind right away so that when you see it later on, you'll come back to you. Okay, so first let me start with a very simple question. What are the square roots of 1? Okay, it's a very classical question. It's been asked several times. The answer many of you will know is plus or minus 1. It's 1 and minus 1. But how do you think of it? You basically say x square has to be equal to 1, isn't it? This is this equation. X square is equal to 1. I want to find x such that x square is equal to 1. Or basically I want to find roots for x square minus 1 equals 0. Now x square minus 1 factors as x minus 1 into x plus 1. You solve these two, you get 1 minus 1. So this is sort of like a easy way of showing the square roots of 1. There are two of them, 1 and minus 1. Easy enough. What about cube roots of 1? Okay, so the analogy here is quite easy to see that when I want to find cube roots of 1, I have to solve x power 3 equals 1, which is the roots of x cube minus 1 equals 0. Now this also turns out you can factorize. This factorization you can check. This is a very famous identity. X cube minus 1 is x minus 1 times x squared plus x plus 1. You can check that. Now if this has to be equal to 0, x could be 1, that could be possibility, or x squared plus x plus 1 could be, x squared plus x plus 1 could be 0, right. So x minus 1 could be 0, which gives you 1, or x squared plus x plus 1 could be 0, which will give you these two complex roots. Okay. You can solve this and check that these two are the correct roots. So there are three cube roots. One is real and the other two are complex, and the complex occurs in conjugate pairs, right. Why does it have to occur in conjugate pairs? Because the coefficients of all these this polynomial, they are all real. When you have polynomials with real coefficients, if there is a complex root, its conjugate will also be a root. Okay. So why is that true? So for instance, if x is complex, x squared plus x plus 1 is 0, you simply take conjugate on both sides, you get x bar square plus x bar plus 1 is equal to 0. So if a complex root is there, its conjugate is also a root. So you see that this and this are conjugate pairs and they are roots. Okay. So this is cube roots of 1, easy enough, you might have seen it before, but this is how it works. Now I may want to generalize what are the nth roots of 1. Okay. And instead of just stopping at 3, I might want to go 2, 3, 4, 5, 6, 7, 8, so on, 200, 300, whatever. I mean, keep going with them. Okay. The answer at one level is very simple. It's basically roots of x power n minus 1. I am able to find one root quite easily, right, which is 1. What about the other roots? It seems like some complicated equation may come, I may not be able to solve it. It looks like all sorts of confusion is here. But what do I know for sure from the fundamental theorem of algebra? This is a degree n polynomial. It should have n complex roots, right? That much I know. So is there an easy way, is there a quick way of finding the n complex roots of this equation? X bar n minus 1 equals 0. 1 we can find very easily, okay? And maybe in some special cases you can find, maybe x power 4 minus 1, you know how to factor, etc. But in general, what are the nth roots of unity? Okay? So it turns out complex numbers in the unit circle give you a wonderful answer for this also. Here is how to think about it. Okay. So here's the unit circle and I have my 1 here and I'm asking for nth root of 1. So first root, nth root of 1 itself is just 1, right? This is easy enough to find. Now, if I go around this circle once, I see that 1 is also equal to e power I 2 pi. Okay. So I may ask for the nth root of e power I 2 pi, which using my complex arithmetic I know is e power I 2 pi by n. Okay, so this is interesting. Now see, I got nth root of 1 to be 1, and since 1 equals e power I 2 pi, instead of 1 I can write e power I 2 pi, but then the nth root now becomes different. Okay, the nth root is e power I 2 pi by n. Now this is very easy to visualize in so many ways. Remember, I 2 pi by n will be some angle here, right? Say 2 pi by whatever, 5, 6, 7, whatever, some angle here, no, 2 pi by n. Now if you multiply it with itself n times, which is the raising to the power n, right? 2 pi by n will become 4 pi by n, 6 pi by n, like that, right? Like that, finally, if you do n times, you will come back to 2 pi. Okay. So 2 pi by n, e power I 2 pi by n raised to the power n is actually e power I 2 pi, which is 1. So e power I 2 pi by n is a legitimate nth root of unity. And notice how the unit circle gives you that wonderful relationship, right? E power I 2 pi by n. So you might think this is the only other nth root of unity I can find with the unit circle. It turns out that's not entirely correct. You can keep repeating this. Not only do I know about e power I 2 pi, I also know e power I into 2 pi is also 1. Okay, if I go 2 circles, that's also 1. So this gives me another nth root, e power I 2 into 2 pi, e power I 4 pi by n. Now 4 pi by n may be somewhere here, and then you go around it, you will go around twice, and then finally when you raise it to the nth power, you will get to e power I 4 pi, and that will be 1. Okay. So now this can be another nth root of unity. So like this you can keep proceeding 3, so on till n minus 1. You can go all the way up to n minus 1. Okay. So, e power I into n minus 1 2 pi by n is also an nth root of unity. So, how many roots do I have now? I have 1, and then I have 1 into 2 pi, 2 into 2 pi, 3 into 2 pi, so on till n minus 1 into 2 pi. So, n minus 1 guys, n minus 1 plus 1, I have got my n roots. Okay. So, to find the complex nth roots of unity, this x power n minus 1 roots of x power n minus 1 equal to 0, this e power I theta, the notion of this and the connection with the unit circle, extremely crucial and very simple. You do not have to work at all, you get the answer. So, the nth roots of unity can be quickly written down in this fashion: e power I 2 pi k by n, k equals 0, 1, so on till n minus 1. Now, what happened to the 1? How did I get the 1 here? If you put k equals 0, here, you get 1, right? This 1, I mean, everything else is not 1 clearly, but this 1 you get with e power I 2 pi 0 by n, so that gives you 1. Okay, so these are all the complex nth roots of unity. Okay, you may ask, they have to occur in conjugate pairs. You will see that this guy and this guy are actually conjugates. Okay, you can prove that, this n is e power I n into 2 pi by n minus I into 2 pi by n. Now, n into 2 pi by n is actually e power I into 2 pi, that is just 1. Okay, so you get that this is actually e power minus I into 2 pi by n, and these two are conjugates. Like that, I into n minus 2 into 2 pi by n will be conjugate with this guy. Okay. So, all these properties you can quickly prove. So, the conjugate pairs will come. I will show this, I will illustrate this later on with an example also. Okay. So, I hope you see this wonderful and simple method of doing complex nth roots of unity. This e power I into 2 pi k by n is very useful in filter design and thinking of Fourier transform, discrete Fourier transforms and all of that. So, it will come back later on when you study digital signal processing and those kind of topics. But this is a very basic and simple idea about nth roots of unity and their connection to the unit circles. Now, all these points are on the unit circle, right? All of these guys are on the unit circle. So, here is one particular example just to show you, very simple example. N equal to 4 ends up being really simple. You have got 1 and you have got e power I into 2 pi by 4. Now, that is exactly pi by 2. So, you have just I, and then I into 4 pi by 4, that is just e power I pi, that is minus 1, and I into 6 pi by 4, that is e power I 3 pi by 2, it is minus I. So, for 4 you see 4 equidistant points on the unit circle. Now, if you do 5, you will get 5 equiangular points, right? You will get 5 of them. They may not be on this axis, but you will get 5. For 6, you will get 6 of the points, including 1. 1 will always be there, and you will get these 6 equidistant points, equiangular points. Okay. So, I hope you see this picture. You can make these pictures quite easily. So, you get for any n, all the nth roots of unity are e power I 2 pi k by n. They are all on the unit circle. Okay. Very useful, very interesting connection. Okay, so let me focus particularly on the cube roots of unity. I have put all of them here. Let us start with this picture here. The cube roots of unity are 1, and then you have e power I 2 pi by 3, and then you have e power I 4 pi by 3. Those are the 3 cube roots of unity. Now, we also seen a calculation earlier, this we saw earlier, right, that cube roots of unity are actually 1 minus 1 plus root 3i by 2 and minus 1 minus root 3i by 2. Now, minus 1 by 2 comma root 3 by 2 will be this guy, right, e power I 2 pi by 3. So, you can quickly identify that is e power I 2 pi by 3 is actually minus 1 plus root 3i by 2. Likewise, e power I 4 pi by 3 has to be minus 1 minus root 3 by 2. So, this is in the third quadrant, this is in the second quadrant, you can quickly identify from here. So, this e power I 2 pi by 3 has to be equal to minus 1 plus root 3i by 2. And e power I 4 pi by 3 is equal to minus 1 minus root 3i by 2. Okay. So, these are the two angles 4 pi by 3. Hopefully, you see the cube roots of unity. So, this is the relationship that you get. Okay. So, cos 2 pi by 3 has to be equal to minus 1 by 2 and sin 2 pi by 3 has to be equal to root 3 by 2. Now, 2 pi by 3 is actually greater than pi by 2. So, you can write 2 pi by 3 as pi by 2 plus pi by 6 and use the formula of pi by 2 plus theta. If you do that, you see that this actually becomes equivalent to sin pi by 6 equals half and cos pi by 6 equals root 3 by 2. So, now this is a very famous well-known sin cos angle. Sin 30 degrees is 1 by 2, cos 30 degrees is root 3 by 2. Likewise, you can also use some other relationship here to find sin pi by 3 is root 3 by 2 and cos pi by 3 is 1 by 2. Okay. So, there are various ways to get this. I mean, once you know this you can use any of the identities to get this. So, this is a very famous well-known cos sin pair, half and root 3 by 2 and half, and that you can quickly see, and that comes from the cube roots of unity being like this. Okay. So, there are various other ways to derive this. I am just showing you one particular. You can start at pi by 3 and then see the 3 times pi and all of that, and you can use various methods to come up with this. I am just showing you that this is one easy way to see it. Now, this cube roots of unity satisfy x cube minus 1 equal to 0, and that is also very powerful. Okay. So, of quick problems, a few set of problems using trigonometric identities and cube roots of nth roots of unity. Supposing I tell you cos theta is 1 by 5, how will you find cos theta by 2? Okay, it's a very standard high school problem. You use the cos 2 theta formula. Cos 2 theta is cos square theta minus sin square theta, and then you use sin square theta as 1 minus cos square theta. So, you get 2 cos square theta minus 1, and here you put theta equals 1 by 5 and theta by 2 is, you will come by solving that quadratic type equation. Okay. So, it's a very standard formula. I am not going into details here, so hopefully you can do this. Okay, so let's look at this. Omega equals this omega or w equals e power I 2 pi by 3. So, this is also a very commonly used notation for this e power I 2 pi by 3. You have been asked to find 1 plus omega squared. So, you can try this. This is not too hard. Okay. So, omega equals e power I 2 pi by 3. It is also the root of 1 plus x squared. So, you can quite easily check this, but anyway, let me just do this for you from scratch. It will be 1 plus omega is e power I pi by 2 pi by 3 plus e power I into 4 pi by 3. Okay. So, you can use these identities in so many different ways. I will just show you how it is done one way. 2 pi by 3 plus e power minus I 2 pi by 3. This is z and z star, right, z bar, right. This is the conjugate, and you are adding the two conjugates. So, you will get 1 plus 2 times cos 2 pi by 3, and you would have seen cos 2 pi by 3 is minus half, right. So, this is minus half. So, you get 0. There is various ways to quickly see that this is 0. So, remember, so this is a cube root of unity, which means omega power 3 minus 1 equals 0, and this will factor as omega minus 1 into, omega or w plus 1 equals 0. Now, clearly w is not equal to 1, which implies w square plus w plus 1 equals 0. So, it is also a quick way of doing it. This is another way of doing it. I am just showing you all the possible ways in which you can proceed. Now, what about w per 100 plus w per 101 plus w per 102? It sounds very fancy, but this is actually the same as this. Okay. You may not believe me, but check why. Because omega per 3 is 1. So, if omega per 3 is 1, omega per 100 is actually omega per 99 into omega per 1. So, what is omega per 99? 99 is 3 into 33, right. So, it is omega per 3 raised to the power 33, and omega per 3 is 1. So, omega per 99 is just 1. Okay. So, this just becomes omega. This is just omega squared, and this is also omega per 3, which is also 1. So, you get 1 plus omega squared. This will also become 0. Okay. So, do not go around evaluating sine and cos and all too much. You use the property that omega per 3 is 1. Okay. So, okay, so that is 1, and here is this x power 5 minus 1. Okay. So, this I was mentioning how you can identify conjugate pairs in the roots. So, let us try it for x power 5 minus 1. Okay. So, let me do that. Okay, anyway, first see the question. The question says, write x power 5 minus 1 as a product of a degree 1 polynomial, real polynomial, and 2 degree 2 real polynomials. So, let us try that. Okay. So, x power 5 minus 1 is so you can write it as, see, what are the complex fifth roots of unity, right? These are 1, e power I 2 pi by 5, e power I 2 into 2 pi by 5, e power I 3 into 2 pi by 5, e power I 4 into 2 pi by 5. So, all this writing up this 2 pi by 5 and all is a bit painful. So, what people usually do is, you write this as omega, and this becomes omega squared, this becomes omega per 3, this becomes omega per 4. This is just shorthand notation just to make your life easier, so that you can write this as x minus 1 into x minus omega into x minus omega squared into x minus omega per 3 into x minus omega per 4. Okay. So, this is the first step in this. Now, these are all complex. So, I have not achieved the thing of one this is degree 1 real. Okay, so this is okay. Now, how do I make these into degree 2 real polynomials? There you have to identify a very important fact. Now, look at this omega power 4, e power I into 4 into 2 pi by 5, I was mentioning this briefly before, is the same as, write 4 as 5 minus 1, okay, 2 pi by 5. There is a good reason why I am writing it, you will see that clearly here. Now, the 5 and 5 will cancel. If you multiply this out, you will just get e power I into 2 pi, right, minus I into 2 pi by 5. That is the same as e power I 2 pi times e power minus I 2 pi by 5. Now, what is e power I into 2 pi? This is just 1. So, this becomes e power minus I 2 pi by 5. So, omega power 4 is actually omega bar. Okay, a very similar calculation will show you omega squared is omega cubed bar. Okay, a very similar calculation. So, this omega power 4 and omega are conjugates of each other. So, let us combine those two things. So, what will happen if I do x minus omega times x minus omega power 4. Okay, so this is the critical combination here. So, I am combining x minus omega, these two I am multiplying together. I will get x squared minus omega plus omega power 4 into x plus omega power 5. Check that out. Okay, so, you will get omega plus omega power 4 into x plus omega power 5. Now, omega power 5 is 1. What is omega plus omega power 4? Remember, omega power 4 is a conjugate of omega. So, this is equal to omega plus omega bar, which is 2 times the real part of omega, right. So, if you do that, and real part of omega is 2 times cos 2 pi by 5, it is clearly a real number. So, this product actually becomes equal to x squared minus 2 cos 2 pi by 5 into x plus 1. Okay. So, a very similar calculation will show you x minus omega squared times x minus omega power 3 is x squared minus omega squared plus omega squared bar into x plus omega power 5, and that is just x squared minus 2 cos 4 pi by 5 x plus 1. Okay. So, this product, these two you multiply together, these two you multiply together, because I identified complex conjugate pairs as roots. So, you will just get x minus 1 into x squared minus 2 cos 2 pi by 5 x plus 1 times x squared minus 2 cos 4 pi by 5 times x plus 1. Okay. So, this is a very nice relationship to have, and one can generalize this. It is mentioned here, generalized to x power 2k plus 1 minus 1. So, you will get x minus 1 times the product of k degree 2 polynomials. You just identify the complex conjugate pairs, multiply them together, and you will get that. Okay. I hope this is clear. So, if x power 2k minus 1 is a little bit more complicated, you will have one more real polynomial, right. You will get x plus 1 into x minus 1, and after that you will get a very similar sort of expression. Okay. So, you see how this complex nth roots of unity play with the polynomials, and using the unit circle one can do very quick calculations. Okay. So, this sort of concludes our study of the complex numbers in this first course. We have not done too much in detail, but I mean this is mostly at school level, little bit more beyond that, but hopefully it was a good quick review for you, and you saw particularly the development of the complex exponential and Euler's formula, and all of those are really wonderful, and e power I pi equals minus 1 is a fantastic result as well. Okay. Thank you very much.